Let us discuss a question on journal bearing. So what is given is we have a journal bearing, okay, basically which is a radial bearing, and you have a shaft. So the clearance I have drawn it very big. Okay, there is one correction. I mean, this is not diameter, the radial. Okay, so as the shaft rotates, okay, this is a constant clearance. There is a constant clearance between the shaft and the bearing. Okay, and so as the shaft rotates, so let's pick any point. Let's pick this point. This has a velocity u in this way, and this is the clearance. So because of the fluid present, there are the fluid opposes because of the viscosity, and this is called the shear resistance. Okay, this is called the shear resistance. So at this point you have a shear resistance called tau, and tau is given by as the shear resistance. Mu is the viscosity and u is the linear velocity at that point by radial clearance. Okay, so here you have the radial clearance. So now this is Newton equation for viscosity. So because of the motion here, how much torque I need to apply for a constant motion, that is the question. So thereby, so let me explain you first what happens. Like when you apply a torque, okay, there are these shear resistance get set up because of the fluid around the circumference, and these shear stresses, the result of these shear stresses is a constant opposing torque. So if your torque is equal to the constant opposing torque by the shear resistance, okay, if your torque applied is equal to the torque which is due to the fluid reaction, then the body moves with a constant velocity. So as you can see, the entire work done by this torque will go into the viscosity. So the entire work done by this torque or the power generated because of this torque will go into the heat generated. Okay, so this is basically the heat generated, because this is done to avoid friction, and friction generates heat. Okay, heat generated. So heat generated is 2 pi nt by 60. So we need to find out the torque. Now torque can be found out by relating the shear resistance to the velocity and clearance. So this is the shear resistance. Now this shear stress is same throughout. So shear stress into area is basically the force. Okay, so or you can do one thing, you can just take a point, simple point. So let's do like this. So as this is rotating, so if I take a small point, the shear resistance is like this. Now the shear stress into this is shear stress into this area dA. Okay, that is the force. Tangential force into radius r is the torque. Okay, so this is the resisting torque d theta because of small area dt. Now this tau is something which does not depend on the area. So if I want to find out the total torque, that is nothing but tau into dA into r, and remember that tau r is something which does not depend on the area. Okay, now dA is same throughout, r is same, so tau into r we can take out common, integral dA. dA is the entire surface area. So tau, let's substitute mu, velocity which is u by c into r, and dA is the entire surface area which is pi d into length l. So now the velocity, how do you get? Because it rotates with it moves with constant speed, so linear velocity at anywhere is r omega, and that is nothing but omega is again 2 pi n by 60. So 2 pi n by 60 into r. Okay, and r is, so we can write pi d n by 60 is u. So once we substitute it here, we get torque. So mu pi d n by 60 by your c which is radial clearance into radius pi dl. So this is entire thing is your torque, total torque that is required. Okay, so let's substitute the values. Okay, so let's first substitute the values. So mu is given as we'll substitute everything in Newton meter. So mu is given as 0.00981 into pi. Diameter is given as 50 is diameter, 75 is the length. So 50 is the diameter, 0.05. N is 750 by 60. Radial clearance is given as 0.07. So 0.07 is the radial clearance. Okay, so into 10 power 3 into 10 power minus 3, because we want to convert everything into Newton meter. So 0.07 is the radial clearance, diameter is 0.05. okay, and here you have radius, which is again diameter by 2, which is 0.05 by 2, okay, into pi, diameter 0.05 into length 75, so 0.075. so this value if I calculate, I get closer to 0.081 Newton meter. Remember, this is Newton meter, not Newton mm, because everything we have converted into meters. So 0.081, close to 0.081. And now the power, because heat wasted is the power generated by this torque, so 2 pi nt by 60. And if you substitute 2 pi 750 by 60 into this torque 0.081, we get 6.36 watt. So this much watt is required for this uniform motion, and this entire thing is gone into the heat generated. Okay, so 6.36 is the answer. Thank you.